Welcome and hello. This is a video tutorial in the FHWA hydraulic toolbox. In this lesson, we're going to be talking about bridge scour calculator, specifically giving an introduction. So I'm not going to be going into too much detail, but this is definitely the starting place, the first video you want to watch on this topic if you're interested in learning about bridge scour calculator. All right, so what I have on the screen here is the FHWA hydraulic toolbox. I'm working with version 5.4.0. Here is my project in the Project Explorer, and I have a number of calculations and analyses already performed. This last one is bridge scour analysis. So the way to add a new bridge scour analysis to your project is to come up to the calculators menu and then click on bridge scour analysis. So I've just added another one right here, bridge scour analysis 2. You can right click and rename it. So I might just call this bridge scour 1. And then boom, this is my bridge scour 1. You can double click to open up the calculator, or you can right click and click on bridge scour analysis from the context menu. All right. A couple other ways to add the bridge scour analysis to your project would be to click on the button, this one right here, new bridge scour analysis. I'm not going to do that because then I'd have to delete it. And then also you can just right click on your project and then from that context menu, select new bridge scour analysis. This tool will compute the scour around bridges specifically following 4 different methods. There's long-term degradation, contraction scour, pier scour, and abutment scour. We're going to look at all those briefly in this lesson, but in more depth in later lessons. Bridge scour refers to the erosion of riverbed and stream bed material around a bridge foundation, such as the pier, abutments, or embankments that is caused by flowing water. So what we want to do here is measure and hopefully reduce erosion around bridges, which is the whole point of running calculations on bridge scour. In this lesson, I'm going to be referring to the user's manual. It's a PDF document. You can also download it yourself if you just come up to the help menu and click on hydraulic toolbox user's manual. Okay, it'll open up as a PDF, which is right here. I've got this one opened up to chapter 15, bridge scour calculator, where we talk about bridges and scour. And then there's a couple other documents we're not going to be touching on in this lesson per se, but in later lessons involving bridge scour, I'll probably just mention this now, is the Hydraulic Engineering Circular number 18, Evaluating Scour at Bridges. And then the other one is Hydraulic Engineering Circular number 20, Stream Stability at Highway Structures. So I'm going to go ahead and leave a link to download these 2 PDF documents in the description of this video. So here we are, bridge scour calculator, and I'm on page 68 here. Here is an image of a bridge. The different parts of a bridge is the bridge deck that's across the top. Then we have the left and right abutments that are on the ends. And then you may or may not have piers that are mid-span supports for the bridge. What I'm going to do in the first half of this lesson is touch on some of the highlights within the user's manual, and then we'll head back over to the calculator and get started with what I'm calling an introduction. All right, so here is the bridge scour. Here's an image. There is main channel definition where it talks about the main channel. So looking down on a channel here, we have these green lines. This is the plan view, and then this is a front view right here. So for a channel, we may have a left bank and a right bank. The main channel is the flow between the left and right bank. And then any flow that is outside of the bank is considered overbank or sometimes considered floodplain. So you could call this the left overbank and the right overbank, which would still convey flow, but just excess flow, typically during large storm events. During normal events, you'd probably just have flow within the main channel. So this right here could depict a flooding event. All right, typically when looking at a front view, we're going to consider this the left and this the right, and that we're looking in the direction of flow. So the flow is going into the screen. All right. Also, the user manual mentions that you may need to know whether or not that main channel will meander. So in the left panel here, figure 15.4, we have a left and right bank that's pretty much centered within the bridge. However, in the right panel, it looks like that main channel has sort of meandered over to the right and centered itself on this right here. Right, next page down, we have the 4 different mechanisms that bridge scour can occur. There's long-term degradation, contraction scour, pier scour, and abutment scour. So then the user manual goes into a little bit of discussion about what these four mean. So I'll just touch on those real quick. Long-term degradation is first. This is the degradation of stream over a long period of time instead of one single large storm event. And it uniformly lowers the stream bed elevation. So what you're seeing here, if the flow is most likely in this main channel, we have a original stream bed elevation, this thin black line, and then we have the stream bed elevation after a long period of erosion, which is this line down here. So it looks like it's about an equal depth. This image is a little bit off-putting because the water level is way up here, when in reality, 99% of the time, the water level will be in the main channel. Further down, it mentions the different methods that are going to be used for this long-term degradation. And these 3 bullet points is something that's a little bit too detailed for me to talk about in this introduction video, but we will be talking about these methods in the detailed lesson when we talk about long-term degradation. Okay, the next method or type of scour is the contraction scour. Contraction scour results from the unconfined stream being constricted as it flows through the bridge crossing. So here's the image right here. It applies to the entire cross section, but a little bit more scour would occur at deeper depths and at higher velocities. So you can see that it's no longer a constant depth. It's a little bit deeper scour occurring at this deeper depth of the water surface, which most likely will have higher velocities as well. And then next is pier scour. As stream flow passes piers, it causes turbulence in the water. The turbulence increases scour immediately surrounding and following the pier. So it's concentrated scour just at that pier. We have a left pier, we have a right pier. I don't know if you can see it too well, but there is a very thin black dashed line here, and also here on the right pier that represents the original riverbed elevation without any scour. But this pier scour has caused a considerable amount of material removal at the left pier and even more so at the right pier. The left pier right here, this is one reference system called local scour reference, where you're measuring basically the distance down from the original stream bed elevation down to where it is now. And then this right pier scour is using what's called Thalweg scour reference. So what you're doing here is just measuring the difference in elevation between the Thalweg of the channel and the depth of the pier scour. Then here are the different methods. Again, we'll talk about that in a little bit more detail in a later lesson. Finally, we have abutment scour that refers to the scour that is closest to the abutments. So here is our bridge deck again at top. Here's the bridge deck. Here is the left pier, the right pier. Here's the left abutment, and here's the right abutment. And you can see in this situation, we have a lot of abutment scour because here is the original stream bed elevation in dashed black line. And then you can see there's been a lot of erosion just adjacent to the left and right abutments. All right. Okay, let's scroll down here. I'm on page 74 now. Again, this is the bird's eye view, the plan view. Flow is going upward on the page. Here is the bridge. And then here are the flow lines. You can see the green lines here representing the main channel. It looks like they don't continue up all the way anymore. At the bridge, there's what's called a constricted cross section. And then further upstream from the bridge, there's called a upstream cross section. That's this red line right here. The upstream cross section is defined as basically the cross section that's upstream of the bridge. However, it's the smallest distance upstream of the bridge where the flow in the river is not affected by the bridge constriction. And then the last part of the user manual I want to point out before we get to the actual project is right here. It's flow as it approaches a pier underneath the bridge. As flow approaches a pier, the water will diverge. The measurements for the pier, such as the angle of attack, should be taken before the divergence begins. This red line represents the direction of the vector of the flow heading directly towards this pier. And then you can see as the water approaches the pier, it starts to diverge to the side. Okay, let's go ahead and head over to the toolbox now. Here is Bridge Scour 1, right click, Bridge Scour Analysis. And then here is the calculator. The first thing we want to do is enable scour plot options. What this does is it allows us, the users, to import a HEC-RAS geometry file, or specifically a project, and then certain elements from that geometry, such as the bridge, which has piers and abutments, will be loaded into our calculator. So this is a little bit beyond what I'm going to cover in this lesson. In the next lesson, I'll probably talk about creating the HEC-RAS file. In fact, if you haven't used HEC-RAS before, it's a little bit unfair to show you everything that there is to show you in HEC-RAS. But say, for instance, we have a river reach right here. By the way, this is a 1D steady flow model that I built just for the purpose of demonstrating the Scour calculator. The cross sections in this river reach are shown in the plot over here. So this is river station 0, 200, 400, and 600. And then I have a bridge that's right here at river station 300. Here is the cross section at river station 0, 200, 400, and 600. And then if I want to bring up the bridge properties, here's the bridge itself, which I've already drafted in. Here is the bridge deck. Here are the 3 bridge piers that I added. Here's the main channel. Here's the left and right overbanks, respectively, and the left and right abutments. So you can go ahead and add and edit that data using the tools over here. Again, I don't expect anyone to know this. If you haven't used HEC-RAS, check out the next lesson. I'll probably describe exactly what I'm doing here. All right, so anyway, after you've created your HEC-RAS file, what's important is that you have this geometry file, which I've saved in this particular project. It's just project.g01. That's the name of the file. So when you have the HEC-RAS geometry already set up, then what you're going to do is import geometry from HEC-RAS file. So make sure you have this checkbox checked next to enable scour plot options. Click on import, and now it brings up a dialog box that asks us to navigate to the HEC-RAS project file name. It's a .prj file, so let me just go ahead and do that real quick. I built it in 6.6. Here it is. Okay. So here is my HEC-RAS project, and what it did is it read the different cross-section data, and bridges. So the approach cross-section is going to be river station 600, and then the bridge cross-section is going to be river station 400. And finally, the bridge itself should be at 300. Boom, there it is. After selecting the bridge, I now need to make sure it knows the correct abutments. It looks like it already has the 3 piers, which is at cross-section station 30, 75, and 120. And then for the left and right abutments, I need to make that selection. 0 and 1 is for left and right. And I can also view the data to confirm that that's what I want. So the left abutment, if I click view, yes, that is the correct data that I used for HEC-RAS. And then the right abutment is right here, and that is also correct. Okay, so that looks good to go. I'm going to click OK. Now a number of the Scour methods have been expanded. I can just toggle those off by clicking on the checkbox. I will hide those sections if I don't want to calculate that specific type of Scour. Not a problem. All right, so next up, we're talking about the different scenarios. Scour scenario is just the name of the default scenario. So what I'm going to do is I'll call this, how about flow rate 500 CFS? I'll just go Q equals 500 CFS. That's the name of my first scenario. And then if I click on create, it gives me a second scenario to select. So this is the first scenario. Here's the second scenario. I'll go ahead and give that a name. I'll call that Q equals 1000 CFS. Okay, enter. And now I have 2 different scenarios. I could add multiple scenarios. I mean, more than 2 if I want, or just 1 is fine. But the purpose of the scenarios here is now I can use one HEC-RAS geometry, but multiple scenarios. So if I wanted to add yet a third scenario, I could click on create. And then here is the third scenario. It's just called Scour scenario 3 by default. But I could give that a name. It could be flow equals 2000 CFS. I'm not going to do that though. I am going to demonstrate how to delete it by selecting that scenario and then clicking delete. Boom, now we're back down to 2 scenarios. All right, so as mentioned before, we can just check on the different types of Scour that we want to add to our analysis. Long-term Scour, degradation, contraction Scour, local Scour at the piers, and the abutments. So if I wanted just to use long-term degradation for my Scour, I'd go ahead and click that. And then I'd click on the define button. And now we have a few more options to put in, such as the method at the top, and then some input data, and then the results. Now that is the same format and pattern used for all 4 of the different types of Scour. So for instance, if I click on contraction Scour, checkbox on, click on define, have to, at the top, select the method and then input some parameter data. And then down below, we'll have the results. Okay, so again, that's a little bit too detailed for what I want to cover in this introduction video on Bridge Scour, but just giving you a heads up, that's how it works. At the very bottom left of this dialog box, there's a button that says Bridge Scour Summary Table. And what we'll see in this table are our results. There will be one column for each of the different scenarios. So here is Q equals 500 CFS, Q equals 1000 CFS, and then there's units, there's the different types of scour that we asked for. Of course, this data is not complete because I haven't added any scour information. All I've done is uploaded the geometry. But I'm just pointing that out, that this is where we'll be finding some of the results. There's also a button to plot preview. That's grayed out for me right now for some reason, as well as bar plot scour depths. No information there either, but that's where we'll be looking at some of our results. All right, well, that was it for this lesson. What we talked about was Bridge Scour in the FHWA hydraulic toolbox. This was just a introduction lesson, so we'll be definitely adding more lessons specifically about the different types of scour, the input, the results, and also building a very simple HEC-RAS model so that you can import the geometry of your river.